So, today this is our third lecture. So, in that lecture we are going to start with the level of abstraction, then the VLSI design style, and then after we will see the packaging. Okay. So, what kind of packaging we are using, that also we will see. So, in the first we can see here that this level of abstraction are segregated in different levels. So, we will see one by one, either we can take top bottom approach or either we can go for bottom top approach. So, as you can see that this is our system. Okay. If we talk about from top to bottom approach, then what are the different blocks we are going to discuss, that we will see. So, first in the system that we are having a integrated circuit, in that we are having a different number of transistor. Okay. So, combining all kind of functionality together in a particular IC is called a total system, that we can say. Now, beside that, what are the things we are having in that particular system? So, in the second we can see the module. So, this module can be embedded inside this integrated circuit. So, this module can contains multiplexer, demultiplexer, okay, these different kind of things, adder, subtractor, kind of different modules is there inside your system. Apart from this module, what are the things we can expect to have in this module? So, these are the gate. So, different kind of gates is used, or a combination of gate can be used to make a different module. Okay. So, it can be AND gate, it can be OR gate, it can be NAND gate, or it can be NOR gate. So, different kind of gates if have together, then it can be act as a particular module, that can be adder, subtractor, or multiplexer. Now, next is circuit. So, by using this circuit or the circuit level of implementation, we can design such gates. Okay. So, this circuits is a combination of NMOS, this is your NMOS, and PMOS. So, this is called a complementary metal oxide semiconductor, right. And the last one is you have a device level, where you can see we are having a different materials to create one transistor. So, you can see it, we are having a source terminal, we are having a gate terminal, we are having a drain terminal. Below this gate terminal, we are having a thin layer of SiO2, clear. So, this is how we can follow top to bottom approach, or apart from that you can also go for bottom to top approach. You have to first have a material for the device, then you can go for the circuit level implementation. Once the circuit level implementation is done, then you can go for the gate level design. Once the gate level design is completed, then you can merge it and you can make the module, different modules. Okay. Then once all the modules are has been designed, then you can combine all the modules within one IC, clear. So, this is how we can have a level of abstraction. Now, the next thing is regularity, modularity, and locality. Okay. So, these are the things we are going to discuss, as we have already discussed the hierarchy in the last lecture. So, in that particular hierarchy, what we have done, that when you are going to design such a big system, then what we are doing, we are following divide and conquer method. In that particular method, what we are doing, we are splitting particular big task into a small task, until unless we are having a very simplified version of the module, clear. So, that we will see it here, like in that I have also given an example of a 16 bit adder, which is divided into 4 bit of adder, then again it is divided into 4 half bit adder, means one single adder is divided into that, then carry and some kind of thing. Now, in the regularity, that indicates the decomposition process must not produce a large number of blocks, and the block needs to need to be similar as much as possible, clear. Like if I will take the example of 16-bit adder, then if you split those into 4 different modules, means 4-bit adder, 4-bit adder and 4-bit adder, then we can see that we have to only design one 4-bit adder, then we can use the same kind of you can say a module, okay, that shows the regularity. So, it can be a array structure normally that we are using for having a good regularity, because if we have a different number of structures and we are going for a different number of irregularity, then the complexity of the system will increase. So, it is better for from a designer point of view that you should maintain a array structure that has a good regularity, clear. So, similar kind of function that does not require much effort to implement those things. The next is modularity. It means that the functional blocks, okay, which is well defined, which is having a well defined functionality, okay, that shows a modularity, which is having a great modularity. So, modularity design allows the different modules to be designed concurrently and also enables design reuse, clear. The next is locality, means if you are having some modules, so the module connection should be within the modular, so that it won't have much interface with the other modules, like in the particular, suppose we are having a 3 different module, and if you want to have a interconnection within the module, then one module you can take, and whatever the connection you are putting, that should be within one module, it should not have any interaction with the other module, clear. So, the locality of the particular function block should be there, clear. Now, apart from that, we should also have a design style, means each and every person is adopting a different kind of design style, because each user is having their own acceptance of the design. Either the person can design, either the person want to have a circuit that can be implemented fast, but some person want, no, I want a more accurate and more faster processor. For that you should require a lot of time to implement those. So, different techniques they have to opt. So, that we will talk here. So, the depending on the application or the cost of the production, means if you are giving a more time in the particular production, then it will be obviously more costly. Okay. So, depending on the production and depending on the volume, how much product you want to develop. So, that depends, and to obtain the particular design style. Now, there are different VLSI design styles that are followed to implement a chip. So, that we will see what are those styles, okay, and we will also see what are the advantages and disadvantages in the upcoming slides. So, the first one is the field programmable gate array design, clear, and the second one is gate array design, the third one is standard cell based design, and the next is semi custom design, and the final is full custom design. So, these are the different technique which you can adopt based on the application, based on the cost of production and based on the volume of production, clear. So, it is up to you what kind of output you required. Okay. So, based on that we can adopt any one of the design technique. So, we will see one by one all of them. Okay. So, first we will see field programmable gate array design. In that particular field programmable, we are having a pre-designed kit kind of thing, where we can have a programmable interconnect, okay, that we will see in the form of diagram. So, it is a fully fabricated IC chip, okay, that I will show you. This is the fully fabricated IC chip. You can see there are different blocks are there, like a green color, blue color. Okay. So, we will talk about all these different blocks here. So, it is a fully fabricated IC chip in which the interconnects can be programmed to implement different function, means based on the requirement we can switch this interconnect, so that it can connect with the some different configurable blocks, where we are having a different logic gates. So, based on our requirement we can play with the interconnect by mean of programming, and we can implement it. Okay. So, basically it has thousands of logic gate, and we have to implement based on the requirement. We can implement any kind of logic function, that with the help of only programmable interconnect. So, the main component that we can discuss in the FPGA are input output buffers, array of CLB, CLB stands for configurable logic blocks, and programmable interconnects. Okay. I hope you already aware about the interconnect, but I will give a brief introduction about the interconnect. So, interconnect is nothing but a wire that is inside your integrated circuit, that is used to connect the two or more transistor which can carry the information between the transistor, that is called interconnect. So, in simple terms you can say it is a kind of wire, that also we will discuss in the unit 2. So, this kind of prototype like FPGA, which is having already which is a fully fabricated IC chip, that can be used to design a faster prototype which is a cost effective, okay, especially for low volume application. Like if someone want to have a outcome and they want to check whether you are getting a proper output or not. So, that you can design with the help of FPGA. Clear. So, we will also see what kind of steps we are following, how we are going for the design to output, that also we will see. So, the first what we have to do, we have to write a behavioral netlist, okay, that we have to write, that will define a different functionality of the design by using a hardware descriptive language. Okay. Then once you have done a scripting of this netlist based on the functionality, then you have to synthesize this to come up with the gate level design. Then we have to convert this netlist into the gate level design. Once the gate level design is done, then we have to map these logic blocks into available logic cells. So, we are having different logic cells in the FPGA. So, we have to map this thing, and this mapping of this logic blocks into the available logic cells is called technology mapping. Clear. Now, after this we have after technology mapping, the next approach is to have a proper placement of the interconnect to configure a CLB, that configurable logic blocks, and we have to define particular interconnections between the CLBs with the help of programmable interconnect. Now, once it is done, then our task is to generate some kind of bit stream, so that we can burn it into the or burn it or download it into the FPGA by using a kind of Xilinx you can use. Then once you have given a input to your FPGA kit, then the FPGA chip can function as desired as long as the power is on, or until unless you reprogram the interconnect. Okay. That means you have to check the output, the desired output based on your bit stream and the configuration of interconnect that you have done, and that will only applicable until unless the power is switched on for that particular FPGA device, or if you want to modify, you have to reprogram your interconnect. This is all about FPGA. Now, the next is gate array design. Now, in this gate array design, again it is splitted into three categories. One is channeled, channelless, and structures. So, we will see one by one all of this. So, the transistors are fabricated, as you already know, the transistors are fabricated on top of the silicon wafer, but the interconnects are not fabricated by using this technique, gate array design. But in the FPGA, we are already having an interconnect, right, which is programmed, but here the interconnects are not programmed. Just be careful here. So, in this diagram you can see, so we will first see the channeled one. Okay. So, the channeled gate array. So, this is the structure of channeled gate array, where you can see that we are having a different blocks, okay, that are connected in one another in the array form. Clear. In between these cells, we are having a small space. Okay. In between this one, we are having a small space. Okay. So, we can assume that this one as a channel. Clear. And this small box is your base cell, where we are having a transistor. Clear. So, you can see that each transistor are placed in a systematic manner. Clear. So, that you can say the rows of transistor, and this is the channel. Clear. and these small boxes are your input output buffers. Clear? Now, apart from that, as we already seen the channel array, you can also see the channel-less array. You can easily observe the difference between the channeled array and the channel-less array, where we can see we do not have any channel in between the transistor, we are only having a rows of transistor. Clear? So, there are no channel. Now, the last is structured. In that particular structure type of gate array, we can have either channel or channel-less array. Okay, it can be. So, what is the, how we can identify what is the difference? So, in that particular structured, you will have a different blocks over here. Okay. So, different blocks you will see. So, it can be customized based on the requirement. Okay. Apart from this channel, we are having a block over here, customized block here. Clear? So, that is called structure, so that you can change the structure, right. Now, the another type of design style is standard cell based design. Okay. So, as you already see from the terms, standard cell based design. Clear? So, this is a kind of prototype you can say. So, where you can see this is my total area. In that particular total area, we are having standard cell area, we are having a different blocks we are having based on the requirement. So, we are having a different blocks, right. So, this blocks you can say, or standard cells, these cells you can say it is already designed or manufactured, it is already pre-tested, pre-designed, okay, or the characteristics of this standard cell is already tested. So, that is why it is called standard cell based design, and this pre-designed cells are stored in the standard library. So, this sorry, these standard cells includes a different kind of logic blocks like AND gate, OR gate, NAND gate or NOR gate. So, different kind of logic functionality we are having pre-designed inside the standard library. Okay. So, apart from that also we are having a different kind of mega blocks. So, these blocks can be seen here. So, different mega blocks will be here, and this mega blocks you can say kind of a multiplexer, demultiplexer or different kind of function that can done by this mega blocks. So, this all kind of different standard cells can be easily seen in the standard cell library, that maybe you already, if you have done some kind of circuit analysis in the cadence virtuoso, then you can see before designing any circuit you are selecting some kind of, you are creating some kind of library, and in that particular library we are having a different pre-designed components over there. Okay, that also you can see that is already pre-designed, pre-tested, but you can also modify it based on your optimization technique, that also allowed, but these are the standard cells. Okay, that you can see it here. Now, next is full custom design. In full custom design, that means you have flexibility to design each and every components starting from the scratches. Okay. So, the designer do not use a pre-designed standard cell library. Okay. Means whatever the components we are already having in the library, that we are not using in the full custom design, if you want to optimize the performance or the speed of your particular components or the device or the cells. Okay. So, the entire chip has to be designed from the scratches. Clear? As each and every parts are designed, the chips are highly optimized in terms of area, in terms of power, means efficient power we have to make for the circuit, and the delay that we have to reduce by optimizing these things. Now, as this technique uses a fully implementation starting from the scratches, that means we are optimizing each and every components, that is why this technique is much more superior as compared to other design style, but it costs time, huge time is required to implement each and every components. Okay. Yeah. So, this is mainly used for high performance and high volume production. Now, the next is semi custom design. In that particular semi custom design, we are using some standard blocks that is already in the standard library, but the things that we want to optimize that particular cells only we are redesigning, so that we will have a better optimization. This semi custom design will take lesser time as compared to full custom design, but again the performance of this semi custom design is not much better as compared to full custom. Okay. So, full custom is having a higher performance. So, this approach is faster as compared to full custom design, because only a few components we are redesigning. So, the performance is wise, we can say it is better than standard cell, but inferior than your full custom design. Okay. So, in full custom design is always better. Now, we have to talk about the design quality. Okay. So, what are the factor we have to check before going for the actual things in the IC. So, first is testability. Okay. The circuit, whatever the circuit you have designed, that should be fully testable. Okay. The design chips are inserted into a PCB first, and these or the multi chip modules for system application, for different kind of application. Then once the fabricated chip we have implemented on this PCB board, then we have to put some kind of testing bits, and then we have to make the test clear, and it should pass all the specification, all the testing array that bits of array that we are putting in the system clear. So, that it should have a testability. Second is yield and manufacturability, means once the test process is assumed to be flawless, once we have given all kind of bits of input, and we know that yes, we are getting the desired output in the testability, then we have to go for the what kind of manufacturability it has, how the yield is there. So, the yield can we find out how we have to obtain the yield, that is the number of good test chip by total number of test chip. Okay. By taking this ratio, we can calculate the yield. Now, the reliability, in terms of we can say the designed chip, design circuit should be more reliable in terms of electromigration. These are the different impacts that we have to reduce: hot carrier induced edging, oxide breakdown, power and ground bouncing, on chip noise and crosstalk. There is huge things inside this each and every terms like electromigration, hot carrier induced edging, crosstalk, that we will discuss in the later slides, but the system should be reliable to and it should be more immune to all these points. Okay. The last is technology updatable. Okay. So, whatever the chip we have designed, the chip products have to be technology update to new design rules. Whatever the new design rules is coming for different technology node, the previous design circuit should be updatable. Okay. It should not like that once we have designed, you cannot transfer to the new technology node. Okay. Even without any changes in the chip functionality. Okay. The chip functionality should remain the same in the previous technology, in the new technology, but it should be updatable, right. Now, the last topic is packaging. In that packaging, the integrated circuits are fabricated on the wafer, that we know that. So, we will see what kind of process we are following. So, in that we have to first a bunch of silicon wafer. Okay. If the bunch of silicon wafer is called lot, okay, this is called lot. If we grab only single if we make only single silicon sheet, that is called a wafer, this is a silicon wafer. Apart from that, if we have if we have fabricated any circuitry in that particular small area, and if we cut it and if we take it out, then these are called die. Okay. Then inside the die you are having some circuitry, then to prevent those circuitry from the other environmental or contaminant things, we have to package this die in a particular chip. This is called a packaging. Okay. So, in addition to protection, the package we are also having a different kind of things that we will see one by one. So, it provides electrical signal exchange between the core die and the outside environment, and and it also act as a medium for heat dissipation. Okay. It provides power to the die. So, these are the different things that we can see it here. Now, the type of IC packaging. So, we are having a two different type of IC packaging. One is pin through hole. In this type of packaging, you can see the pins, the vertical pins are very longer. Okay. That is why it is called pin through hole. Okay. And the second one is we are having horizontal length. So, this one is horizontal, this one is a vertical. So, that is why it is called a surface mount technology. Clear. So, these are the two technology that we are using to package the IC based on the requirement, right. In that PTH, the packaging pins are extended in the vertical direction, so that they can be inserted through the holes in the circuit board. Whereas, in the surface mount technology, we do not require to have a hole, we can put it on the surface of the on top of the surface. Clear. So, these are the two major difference in the pin through hole and the surface mount technology. Yeah. Thank you.